Hello, my name is Bruno Diaz. I'm a fellow in Chile. I'm going to talk about ESO future concerning the galactic archaeology, the Milky Way and beyond. So first of all, how do you observe the early universe? Here it's a good representation of the history of the universe and the evolution of galaxies since the Big Bang up to now. The idea here is to have observations of galaxies at different distance, which means different times to the past. And you can organize, for example, and pick some galaxies that are Milky Way type and organize them in a time scale. Here it's the result. You can see in the right blue galaxies, very small because of resolution. And the left you can see red galaxies more evolved, and their stellar populations are older. And they are also resolved, so you can see spiral arms and etc. The idea here is that for the observatories, the challenge is to observe detailed information as far as we can to understand the different stages of galaxy formation and evolution. So that's exactly what was said in the Tindezo papers from last year. Here he said, the science enabled by the ELT focus on three prominent areas, and one of them is exactly probing the formation and evolution of galaxies by enabling the study of resolved stellar populations in the full range of galaxies out to Virgo cluster distances and in integrated light to high redshift. So here's what it means in terms of images. So you can see in the left, the bright galaxy is our own Milky Way, and the right galaxy, the bright one, is Andromeda. All the other points are small galaxies, dwarf galaxies surrounding our neighborhood. For these galaxies, we already have a lot of surveys running because you can resolve their stars. So for example, for the Milky Way, we have on the upper part the VVV survey and the VVVX now, the continuation, that are basically targeting the inner parts of the Milky Way, which are highly extincted. So we cannot observe stars in the visible wavelengths, we have to go to the infrared. That's exactly what they are doing. They are having many good results already on the only photometry, and they're also providing targets for spectroscopic follow-up. Here in the bottom panels, you have Gaia ESO results and some spectra for dwarfs and giants on the left, and on the right, you have some results on the abundances of magnesium and metallicity, where the colors represent different velocities of the stars. So basically here you are seeing difference between different components of the Milky Way, and with chemistry and kinematics you can do a lot of characterization, understanding of the whole evolution of the Milky Way. If you go to dwarf galaxies nearby, where you can resolve the stars, even the faint ones, in crowded regions or the sparse regions, the idea here is in the right panel you can see the Carina, the color magnitude diagram for the Carina dwarf galaxy, going down to the main sequence turn-off, which is the faintest stars on the bottom. And you see different sequences of points there, which are stars. They represent different ages and metallicities of the stars. On the left panel, the color dots represents different distributions for different stellar ages. And if you compare this with the observed diagram, you can imagine, and with some statistics, you can do a fit and derive what happened to the past of these galaxies on different ages. If you go to very distant galaxies, this is the NGC 5128, Centaurus A, that's the most distant galaxies for which we can resolve stars. And it is the nearest elliptical galaxy, so that's really interesting because it's a different morphological type than that of our own Milky Way. Here I show an example of the color magnitude diagram for this galaxy, at least for the outskirts where you can resolve stars more easily. And you can realize that this is different from the diagram I showed before for Carina, because here it's only reaching down to the horizontal branch, because it's much far away, so the faint stars are not covered. Also, you can see in the left plot, it's an image of this region where the dots are stars and also cosmic rays. There is a lot of cosmic rays because it's large exposure times, If you observe with the ELT, we can reduce the cosmic rays by reducing the exposure times. Here is the simulation of the magnitude limit we can reach with the ELT for this same galaxy. So green area is the best we can do, and the yellow and the red, it's about the limit of resolution. So the horizontal branch is the up dashed line, and the main sequence turn-off, which is our target, is the bottom dashed line. Here in the CMD, the diagram you saw before, it's reaching only the horizontal branch. So you can imagine how it will look like in the future with ELT. Here's the globular clusters from the same galaxy in the same distance. They look a bit different from those we know from the Milky Way, because these tiny squares are only 5 arcsecond size, which is really, really small in sky, and they are really faint as well. So the idea here is we want to observe resolved stars on these clusters as well. For crowded regions, it's even more challenging, and we need ELT to do that. For the near-infrared filters, if you reach a 10 milliarcsecond angular resolution, you can maybe resolve the outskirts of these clusters. And then you can compare their images with the ELT with those you can do with a 4 meters telescope as VISTA for the Milky Way globular clusters. As you can see here on the right, a picture as for 47 Tuc that was seen by VISTA. So with these stars, we can do color magnitude diagrams as we see in the left panel, which is reaching the main sequence turn-off in the horizontal branch. So you can provide ages and metallicities and horizontal branch statistics. This will disentangle all the degeneracy we have currently with integrated light for these distant clusters. If we had blue UV bands and U band filters, for example, you could split the sequence in this diagram, as you can see in the middle panel, and these color points there, and you can identify the different generations of stars that were self-enriched by the cluster populations. This remains true when you look at the chemistry on the chemistry from spectroscopy on the right plot by sodium and oxygen. So the question that remains is if this is true for all galaxies or not. Here you can see the distant clusters of Virgo, that's 65 million light years from us. That will be the limit that ELT will reach to resolve stars. At least on its halo, they're not so crowded, and only for the brightest stars, of course. So far we covered this nearby universe and observed different galaxies, but how can we reach the most distant and look into the past? The idea is that the stellar atmospheres, they have a lot of information. If you go for spectroscopy, you can recover the chemistry of the atmosphere of these stars. Turns out the atmospheres keep the information of the interstellar medium from which they were formed in the first place. So basically, if you observe different stars with different ages, you have a time scale of the chemistry of the conditions from which the galaxy evolved through time. Here I show an example for our own Milky Way, where we have on the left an age and metallicity relation, and on the right you can see this equivalent in this plot that we showed before, the early evolution of the Milky Way. If you do the same for the Small Magellanic Cloud, you have a different chemical evolution and you represent a different range of ages. If you don't have access to the color magnitude diagrams and ages of the stars, you can do a lot only with the chemistry. If you go here for the left panel, have a representative of alpha and metallicity, which gives you the information of the star formation rate, for example. And on the right, you have the points in gray, which are Milky Way, and the color points are different galaxies. And you see different trends. So this means that they had different efficiencies of star formation. If you want to do a very complete scenario of the very early universe and go to the very first stars formed in the universe, you have to go to heavier elements. And for this, we need large surveys with high-resolution spectroscopy and cover a wider range of spectral covered. This includes the blue part. At ESO, we already have some instrumentation cover different conditions of wavelength and resolution, but we need more. So here I show some examples. So VISTA will have foremost, and VLT will have moons, ELT will have high-res and MOS. But for VISTA we cannot reach the faint stars. Moons will have to share its time with different instruments, and the ELT will be very competitive. So the idea here is that we have to fill the gaps with a dedicated spectroscopic telescope only dedicated to surveys. Okay, so my take-home message. We know how to handle large surveys, and we have targets from photometric surveys to go to spectroscopic surveys, but we still need blue wavelength coverage and dedicated large telescope for spectroscopic surveys. And now we can finally understand our Milky Way in comparison with many different other galaxies, as we have detailed information from their stars. That's it. Thank you.